So, hi, I'm Philippe Delandmetter from Utrecht University. So I'm quite new to that field, so you may not know me, I guess. But I work for 1 year at Utrecht with Eric van Seville that you might know. And we are working on the development of parses, which is a Lagrangian ocean particle tracker. And we focus on the modeling of the dispersion of plastics in the ocean. So, yeah, whoops. Here. So mostly the kind of application we want to do, we want to understand what are the main processes driving the transport of plastics. Here I'm talking about microplastics, which is floating microplastics. So it just stays at the surface. And to do that, we release some particles. So here just at the Thames and the Rhine River estuaries, and we just track the plastics following the flow field to see where it goes, and it ends up in the Norwegian coast, in the Arctic, and so on.
It's not coming from just the Netherlands, is right?
So some political reason, maybe there is a lot of trashing going on here. No, but yeah, so there are many processes going to the flow field. Among them, there are some processes which will be shown by the SKIM region, so we want to see what's the importance of those processes, and then how necessary would be all the data we could have from SKIM. So to do that, we use Lagrangian modeling. So a quick reminder, there are two ways of seeing the environmental dynamics. There is a linear perspective, which is used by most of the ocean circulation models. We just study the evolution of some points which are fixed in space. And then there is the other one, Lagrangian modeling. We also follow the evolution of points, but those points are material points. And those can be plastics, but also pieces of water, plankton, tracer, or even a tuna fish. We have studies with when we follow the dynamics of a tuna fish a long time. So basically, what is parcels? We want to track one particle. To do that, we use the output of other models, which are just the outputs of those models are stored on a grid, and then we just interpolate the feed, and then we follow the plastic. So it's quite simple. There are many other Lagrangian trackers. The point of parcels is to provide other tools to be able to interpolate different flow fields easily, so we can interpolate easily the current velocity as well as the wind, the Stokes drift, some temperature. So we can read a whole set of different data sets on different grids, and we want to manage that such that the parcels user will not deal with all those problems. We do that for him. And on the other side, we also manage the particle set. So we want to play with millions or tens of millions of particles. We want to be able to add new particles. We want to be able to have the particles to die or to beach. So we want to have a lot of freedom on the dynamics of the particles. So we also deal that for the user, and he really can focus on the science and not on the interpolation schemes. So given that, what is parcels? Parcels is a Python. It's a Python model. So a Python module is a set of Python classes that enables you to easily load the input data, so the float feed data, and mostly it allows, when you have loaded them, you can custom them easily. So you can, compared to other models, you can easily adapt your data or pre-process your data before the interpolation. And then the other part is the particle dynamics. So you want to be able to set up easily whatever dynamics to your particles. So your particles can just follow the flow field, but it can follow some part of the wind. It can also sink, or it can swim. So the tuna fish were swimming, given some behavior. So we want the user to be able to easily set up these dynamics, and that's the main point of parcels. And then we provide many functionalities and pre-pro and post-processing. I was talking about grids before. So with parcels, we can read different kind of grids. So rectilinear grids, curvilinear grids. In the vertical, we play with Z level, also terrain following levels, and also we can play with different kind of discretization. So when you have a C staggered grid where the U and V velocity are not at the same place, or with a classical A grid. So that's what we can do with parcels. We can read different fields, and then this comes to our application here to the North Sea. So we have different data sets. So mostly we have NEMO, which is a density-driven circulation with some wind, but with no tides. We have some Siemens data in this area for this application. And then we have a Stokes drift and wind drift from WaveWatch 3, which is only available until that region. But I've just learned before, and actually there is also some data for the Arctic, that would help us a lot because it's not so cool. And at some point, we just stop following the Stokes drift. So we have a different data set, and we would like to follow the importance and the importance of all those flow fields. So this is, we have just the Nemo flow field, and then we have the Stokes drift, which is way slower, and the wind field, which is comparable to Stokes at some place and not in some others. So those are the main processes, and then what happens to the dynamics? So first, post-processing, we just release some particles for a few years. So we release, for 1 year, we release daily some particles in this area. We just track them for a few years, and this is the density, the density of the particles after 3 years of simulation, time average over the third year. And mostly, what do we see? We have a lot of accumulation in the Arctic, some plastic, but not so much goes further away. And then we have also beaching on the Norwegian coast. This is one output of one model, only using Nemo. Then again, with this same Nemo, we can just age the particle. So mostly it takes up to 1 year to reach the Norwegian coast. After a second year, it reaches the Arctic, and then it just disperses a bit further, but we don't have so much transport. There is mostly a dispersion. All right, so now let's compare the different processes. So the first one, this is the run we've already seen, so the Nemo run. Then we can compare also with another Nemo run, so it's the same physics, but just instead of having 1/12 degrees, we have 1/4 degree resolution. And this comparison would be interesting to see what's the importance of the resolution, because the SKIM resolution is not fixed yet, right? So we would like to see, but if we can still push to have a high resolution, even better. But still, so resolution has importance. So here, what do we see mostly? With we have a bit more accumulation. We don't see it so much on the screen, actually. Yeah, we have a bit more accumulation here with low resolution, and we don't see so much here, but we see later on. We have also more beaching on the Norwegian coast. Then what's the effect of Stokes? Mostly, as we've seen in the movie before, on Stokes we have a lot of particles. It just immediately push towards the beach. So we have way less particles reaching the northern area. And again, this is with diffusion also. So we just process. We just take into account diffusion by some random walk, and we have much more beaching, especially in the North Sea, way more than we have seen. But we don't see it so well, the comparisons here. So maybe let's pass to another plot. First, let's show this one. So this is another map. Also, this is just the percentage of the plastic which has passed by some area. So 100% or mostly pass, 100% has passed by this area. And then the further north you are, the more yellowish it goes. So here you only have a few 10% of plastic has passed, and there is not so much. And what do we see? We can see that with Stokes and with diffusion, we don't have so much plastics reaching the Arctic. But it's quite hard to, so this is just a visual map, but if you want to draw some budget, what's the proportion of plastic that ends up at some point, it's better to just draw some zones. So those are the 4 zones we've decided here. Like, we just have the North Sea, the Danish Strait, Norwegian coast, and the Arctic. And we have the evolution for time, so we release everything in the North Sea. Then all the plastics passes always has some curves around the Danish Strait before going to the Norwegian coast. And then some get stuck in the Norwegian coast, some reaches the Arctic, and get stuck around there. That was for the Nemo run, and we can compare for different zones the different runs. And that's where it's getting more interesting. We can see what's the influence of the different runs. So what do we see mostly? With Stokes, with diffusion, actually. With Stokes, we have much more beaching, but not so much in the North Sea. So it's diffusion that then leads to the more beaching in the North Sea itself. The effect of Stokes will be mostly accumulation in the Norwegian coast. And what's the difference between the Stokes and wind? So it's not so for the North Sea we don't see any difference. So both lines of those runs are here. They just overlap. We don't see any difference. But in the Norwegian coast you will have more accumulation with the red. So we have more accumulation with wind, less accumulation with Stokes. And this difference will just overlap in the Arctic. So Stokes leads to a bit more transport to the Arctic than wind. So we have a difference on that side. And then we also see the effect of resolution, but also for the resolution, it's mostly also the boundary condition are super important, and all the coastal zones has a very important effect in this area. Now let's go back to a more broader picture. So this is a study that has been done by Victor Oning, which was a master's student last year in Utrecht. Now he just moved to Bern to start a PhD. He ran some plastics using just Ekman transport and geostrophic flows. And then on top of that, he added some Stokes drift. And he wanted to see what's the importance of Stokes drift in terms of the accumulation patches and also in terms of general circulation. And what does he mainly observe? He observed there is much more transport towards the polar zones, so towards the Arctic and mostly in the Antarctica. So we see much more circulation still in the Antarctica, thanks to Stokes drift. So Stokes drift is a very important. Is very important in the Southern Ocean. So we need that. We need it resolved as well as possible to study the dispersion of floating plastics. So again, here we stick to surface plastics. So to conclude it. So here we've seen the importance of we have studied the importance of different processes. We haven't calibrated anything, so we haven't gone with data. We need more calibration, but mostly what we wanted to show is the different processes have importance. We need to compare them, and to do that we've used parsers, which is quite convenient to use different data sets from different formats, from different grids. So we can easily compare those data, and this is necessary to understand better the processes driving the plastics. And mostly, what has to be done now. So we know coastal zones are very sensitive. Here I was talking resolutions. This is quite obvious, but also in modeling we have to watch out how do we process the beaching. So yeah, there are some parameterization for the beaching in the coastal areas. So this is super important, as well as the diffusion. The diffusion is also there is a lot of uncertainties, and there is a lot of discussion how to play with diffusion in Lagrangian modeling, and this is a major problem, a major process for the transport of plastics. And Stokes drift, it doesn't have to be shown. It is shown. Stokes drift is a major actor for the transport of plastics. And in our case, it has a lot of impact in the Arctic region. And that's it. Thank you for your attention.
It's just a comment, and very nice to see that. There was a paper earlier this year in Nature which did a similar kind of work, which was showing that in order to get plastics onto the Antarctic Peninsula, which was crossing, as you say, the ACC, etc., it was only with Stokes drift that you could do this. And of course, that's what we'll be measuring with SKIM. So,
but someone has shown this figure before. Yeah. Fabrice has shown this figure, I think. Yeah. When we see the Stokes, you need Stokes to cross the.
Absolutely.
Yeah.
Absolutely. So that's Eric Van Sabeel and co. who've done a bit of work.
Yeah.
There. Yeah.
Was a question?
Yeah. Okay, Christophe. I mean, maybe I can.
No.
What is the legacy of using Stokes with currents? You just add the currents of the model with the Stokes from wave wash tree, right?
What I did here?
Yeah.
Yeah. What I did in here, it was just adding Stokes to Nemo. But I just added one feed to the other. But for this movie, it's important to see that there are, so on the left movie there is no Stokes, on the right movie there is Stokes, but you have to watch out because actually, so this is Stokes from wave watch 3, but in this data there is already some Stokes. So this is why we say this data plus Stokes, but the way that this globe current Ekman transport was used, it was taken from some drifters, and those are also taken into account some Stokes. So this is not saying there is no Stokes, there is Stokes. It's not super true on that side. So we have to watch out what's said. But in this paper, they discuss what's the impact. So it's why they don't say true current. They say this plus Stokes. You have to watch out.